Hey there, I'm Nix, and today's video is revisiting Pascal's triangle. I'm going to solve this problem in the C++ language and give you a detailed explanation of the entire process, through the planning of the algorithms, to the coding of them, to analyzing their time and space complexities, as well as looking at their LeetCode rankings. If all of that sounds interesting to you, then stay tuned. Welcome back. Now this video is going to go over two different solutions to this particular problem. And as opposed to the previous Pascal's triangle problem, the original, here we're given an integer row index, and instead of returning the entire triangle like in the previous problem, we want to just return that particular row in a zero-index system. So if row index is, say, 3, we want to return the third row of the triangle. So this being row 0, 1, 2, 3, we'd want this row here. And we have now a couple of examples here to drill home the point, and we have constraints that we go from 0 to 33 in terms of our row indexed. Finally, we have a follow-up question, and it asks us if we can optimize our algorithm to use only big O of row indexed extra space. This follow-up is here probably to get people to create other solutions that don't really rely on this prior problem's code. Because a really easy way of solving this problem is to simply take the code that you created from Pascal's triangle here and plop it into here. With just a few tweaks of that code, you would have the ability to just return one row. All you would need to do is create a vector of integers variable to store the row. After you've created the entire triangle, then put your row of interest into that variable and return that variable. Now, that doesn't satisfy the follow-up since you're still using a lot more memory to create the entire triangle instead of just one row, but it is a way to get lovely green text from this problem. But as the vast majority of the code is exactly the same as in the previous Pascal's triangle problem, I'm not going to show that. If you're interested, you can click the link in the corner to watch the video I've created for solving the Pascal's triangle problem to see what that code would look like. Anyway, moving on to planning out the first solution of this problem, instead of carving out all of that memory to create every single row of the triangle, what if we created each row within our row variable and then overwrite that variable with the next row of Pascal's triangle? In other words, bringing up a handy-dandy whiteboard. Initially, let's say we're given 4 as our row index. So our vector is going to have 5 numbers in it. We could carve out all of that space ahead of time and have the first number present in it be 1. After the second pass, we would essentially have the second row of Pascal's triangle present, our values being equal to 1, 1. Our third pass over it would create the third row with the values 1, 2, 1. Then our next pass creates the fourth row, 1, 3, 3, 1 are the values this time. And then finally, after our last pass, we completely fill out our row with the values that are meant to be there. But how do we do that? Well, we'd need a variable to house the row, be a vector of integers. And then to mimic this behavior, we'd have to have nested loops. The first loop is walking through the entire array here. The second one is walking the array in reverse, starting from wherever our current index is and going all the way to the second value. And what it does is it's adding the value of the current index and the value from the index that's one less than that. So looking at this particular step, our current index would be at this 0 here, and then to create the next row, we would have to add 0 and 1 and replace that 0 with the summation of those values, 1. Moving down, we would see a value of 1 and then 2. Summing that up, the value is replaced with 3. Moving over again, we have 2 this time, plus 1, again, being equal to 3. And since this is the stopping point, we never want to overwrite that 1 in the first index that we see. We've got our updated Pascal row. So with 1 vector of integer variable and 2 nested loops, we will create everything that we need. So let's go and actually look at that code. First up, creating the vector of integers, named it Pascal row, and I've set the size to equal row index plus 1. With that variable created, the next thing I do, as when you pre-allocate a size, by default it fills all of the spaces with 0 as a value. I want to replace that first value at index of 0 with a value of 1. So at the end of this code execution, I have this kind of array present, with 1 being the first value, and then a bunch of zeros depending on the row index that we're given. Next are the for loops. The initial loop is going to walk the array from an index starting at 1 all the way to the end of the array here. So I is going to be less than row index plus 1, and increment up I each time. Now for the second loop. This one is also a for loop. This one is going to have j index being equal to whatever I is. It's going to go in reverse, so j decrements every single time, and it's going to go as long as j is greater than or equal to 1. Remember, we don't want to mess with, say, this value. This value is already perfect. Now that we have our loops, the only thing we need to do within those loops is set the value at j index, so Pascal row j, equal to itself plus Pascal row j minus 1. So it'll sum the two values at those two positions and overwrite the value of just a j. Last thing to do is outside of the loops, at the end we'll have our completed Pascal row variable, so we just want to return that. That is all the code that's going to be required for the solution, so let's run it and make sure I didn't make any mistakes. Pending judging finished. Excellent. Let's go ahead and submit and prove that it works. There we go. Green text. Excellent. Now we get to do some time and space complexity analysis. For space complexity, we have indeed fulfilled our goal of creating a big O of row index space complexity. The only variable we've created is that vector of integers, whose size is dependent only on that row index. For time complexity, we need to look at these nested loops, and both of these loops essentially depend on the row index. Since they both depend on the row index and they're nested means they're multiplicative, so we have a big O of row index squared time complexity here. But that's not going to be too bad for this specific problem, considering row index itself is going to be restricted to a very small range of numbers, which means that the distribution of the runtimes on the LeetCode rankings isn't really going to be that much of a distribution, because there's not really much in terms of variation in row index that could help differentiate, say, a big O of n squared solution from, say, a big O of n. But with that said, let's actually look at the rankings now. And yeah, not really much of a distribution here. Looking at the memory, a fairly bell curve-like distribution, and in a very small range of memory. So I'd expect some potential ping-ponging around here as well. Alright, that was one solution for this problem. Let's move on to the next one. In this solution, we're essentially doing the same exact thing as the original Pascal triangle problem. We're creating all of the row values and building up each row based on the values from the previous row. Now that's kind of Pascal's triangles thing, as this little handy-dandy animation shows. But to do that in an in-place array requires nested loops, which means higher time complexity. The question then becomes, is there a way to directly calculate the value of a particular row for Pascal's triangle without having to create all of the other rows? And yes, there is. One way which is less useful for this problem, and one way that we're actually going to use for the second solution. The way that we're not going to focus on so much is the equation for calculating a particular value in Pascal's triangle that uses the n choose k approach with factorials. So up on the screen you should see that equation. So if you know the particular row and the particular value within that row that you want to calculate, you can use those two indexes, n being equal to the particular row index that you want, and k being equal to the specific place within that row that you want to calculate. So for example here, if I want to calculate this particular value in this place, I would want to go to the fourth row index, 0, 1, 2, 3, 4, and I'd want the index of 2 within that row. So 0, 1, 2. So n would be 4, k would be 2. Plug all of that in, calculate all those factorials, and you'd have your value. But the reason why we're not going to use this particular equation is because of the factorials. Factorials very, very quickly become very, very large numbers. So large, in fact, that even if you say use a long variable, it's not going to be big enough to handle what the value of 33 factorial would be. How big is 33 factorial? Well, it's equal to that number. Yeah. Big. That number is not going to fit into an integer, no, just no. And if you can't compute all of the factorial values, you can't divide them to get to a value that actually would be able to fit into an integer value. So that solution is not going to be useful. But there is an equation that is going to be useful for us, namely this one. With this equation, we can create an algorithm that will compute just the values of the row that we want, without having to go through several iterations calculating all of the values from all of the previous rows as well. So with the use of this equation and some variables, we can just have one for loop that goes through the array and calculates each value that's supposed to be there directly, which means our time complexity is going to be reduced because we won't need to use nested loops in the solution. So let's move on to the code and see what that's going to look like. First up is going over the variables that we need. We still, of course, have our Pascal row vector of integers. This is completely unchanged. And we still want to make sure the first value in it is set to 1. But now I've created a double variable called row term, set that equal to 1, and just gone ahead and set the 0th index value in Pascal's row here to that row term. The other variables I need are two other doubles, one being n, the other being k for running the calculation, and I figured I'd just keep the same variable name that is used in the equation. N is going to be equal to the row index plus 1, and k is going to be set equal to 1. Next up is the start of the for loop. And this one is fairly typical. Our index is going to start at 1, and we're going to go as long as that index is less than, well, the end of the array. But of course, I have n being equal to that size. So instead of just saying row index plus 1 here, I just truncated it a bit and set it equal to n. Now for what we want to actually do in the for loop. For every index, we want to go ahead and crunch that equation. In other words, we want to set the row term equal to itself times this term here. So row term is going to be equal to itself multiplied by n minus k divided by k. And again, I don't have to do the n plus 1 here because I essentially have the plus 1 already built into n. So this is exactly equal to this. Now, the next step is this equation only changes by k for each term. K increases by 1 every time. So to do that, you just do k plus plus. Finally, I want to go ahead and assign the index of Pascal's row to that row term plus 0.05. Now, the reason I'm adding 0.5 to the term is to compensate for any rounding errors that come about. That is also the reason, as this comment shows, that I'm using the double. The double's precision in these types of calculations is enough to just be off by a small decimal place. So, as an example, one of the terms when this equation is crunched could amount to, say, 461.97, etc. It's supposed to be equal to 462 in that way, but due to rounding error, it doesn't turn out like that. But to compensate for it, since this row term, a double, is being put into an integer variable, it doesn't care what the decimal place is going to be. All it cares about is the integer portion. It's going to throw away all of the decimal places, and it's not going to do any kind of rounding. So since using these doubles runs a risk of being just shy of the value that I actually want, adding 0.5 to it essentially serves as a way to round the value up to what I need before I place it within the vector. Finally, outside of the for loop, I'm going to return Pascal's row. And with running this code, you'll see that it should work. Pending, more pending, finished. And we get exactly what we want. Even when, say, we go to the maximum limit that we should have, if I put in 33, we see that all of these values should be exactly the value that we want. And they are, all the way to the absolute end. Now I want to show you what potentially happens if, say, this wasn't here. Let's go ahead and put 11 there instead, just so that I don't have to scroll so much. Judging, finished, and look what happens here. This is the example that I was stating earlier. My answer has some of them right, but because of the rounding error that happens, instead of 462, which is what I want, I get 461. Instead of 330, I get 329, and so on and so forth. That is not what I want. So that inclusion of the 0.5 fixes that rounding error. Now, if you're curious as to what happens if these are floats or integers, we can check that out as well. And let's see what happens here. With 11, it fixes this issue. Fine, great, good. What about for the maximum one? Pending, judging, and finished. So what do we have here? Well, looks good so far, but look what happens. Here, my answer has a big number ending with a 9. This one, I'm supposed to have an 8 here. And you see it's off by 1 here, it's off by 2 here in this value, it's off by even more in this number here. Yeah, right here, it's off by 4 here, it's off by 8 here. The rounding error compounds itself. So even floats don't have a big enough storage space to record the value that's being calculated to avoid those kinds of propagating rounding errors. But a double does have enough space. And of course, as you'd imagine, this is going to be much, much worse if you have integers as well. So this is why these are doubles and why this decimal addition is present as well. Now it's time for the full shebang. So let's click the blue button and see green text. For time and space complexities, we technically still have a big O of row index for our space complexity. We do have other variables here with these doubles, but those take up constant space. Our variable space is still dictated by the creation of the Pascal's row, and thus is dictated by the row index. And in big O, we only care about the biggest term, so those constant dependencies fall by the wayside, and we report our space complexity as that of a big O of row index. Our time complexity, however, since we are no longer using a nested loop, we only have one loop, that means our space complexity has reduced to being equal to big O of row index as well, instead of that squared value that we had last time. And with that, the last thing to do is check out the rankings. And of course, we see a huge difference in the distribution in terms of runtime. Kidding. Same exact thing here. And in terms of memory usage, I've seen this particular solution ping-pong around a little bit. So it still has a ranking, it still uses some memory. And with that, that was how to solve Pascal's triangle 2 on the LeetCode website. I hope this video helped you out in some way. If it did, consider subscribing. And as always, I will wish you happy coding and to have a nice day.